even know how the core got formed, and nobody knows what the core is all about anyway. There's only guesswork about the chemical composition of the core. We don't know that that core is iron and nickel, as it's presumed to be. We have no idea. We have no way of measuring that. All indirect evidence, and the supposition is it's iron and nickel. I could probably find a half a dozen or more different element combinations that would satisfy the same criteria and not be iron and nickel at all. So we don't know anything about that. But if we look at these radiometric isotopes, I'm dealing with uranium, the two types, 238, 235. I'm dealing with thorium, samarium is another one that's used, and rubidium and potassium. These are the major isotopes that are used for dating, okay? So I'm dealing with those. This is the amount that's there known to be in parts per billion, as we know it to be now. These are the percent of those isotopes that would be contained in the crustal sample, okay? The number, the net concentration in parts per billion would be these, and then the masses of those in grams for each of those amounts would be these amount of masses, and then the number of atoms of each type would be determined from that. Now, I need to deal with individual atoms because it's individual atoms that get affected, so for the purposes of calculations, we need to know that. You don't need to know that. Now, one of the things about the plasma is we can arrive at the temperature. There are different ways of doing that. This is one way. If you knew the energy per unit volume, which is EV, if you knew the density and you knew the heat capacity, like constant pressure, CP, that combination would give you a temperature. Now, it turns out that this number and this number, these two bottom numbers, D and CP, they're not these numbers right here. That's a mistake. There were wrong numbers that were chosen, and in fact, they should be much larger than what these numbers are over here, okay? So that's a change. Furthermore, this energy per unit volume is not the energy derived from the bulk modulus divided by the volume, because the energy derived from the bulk modulus does relate to the volume. By definition, the bulk modulus is a volume quantity. So if you derive the energy from that, it's already an energy per unit volume. So these numbers would have to be changed. Is this equation wrong? No, the equation's right. It's just the numbers that are wrong. Is the answer wrong? No, the answer's right because you can arrive at it about 2 or 3 different ways. So this order of magnitude of about 10 billion years, 10 billion degrees, 10 billion degrees Kelvin is a right order of magnitude, okay? But I just didn't want you to believe that these numbers were correct here, okay? So this is the result. We have what kind of temperature? An enormous temperature.
Ed, would you define plasma then as disassociated atoms in a high energy state, or how would you?
Well, technically, the plasma is always defined in terms of the individual atoms that have been totally stripped to bare nuclei and bare electrons. Okay, so you've got a sea of these positive nuclei and these electrons. We call these nuclei nuclides, N-U-C-L-I-D-E-S, nuclides. That's what they're called, nuclides. And these nuclides and these electrons make up the plasma. Now, the fact is they're dissociated, so those electrons are not combined with those nuclides anymore. They're all undergoing their independent positions. So the plasma is really not a rigid state. It's a dynamic environment, okay? But trying to treat the dynamics of the plasma and looking at these details is a horrendous problem, and it's insurmountable. So you got to treat it as in like a frozen core, as if these particles were interacting in positions that are relatively stable. And it's not a bad approximation because we use it in the gas laws all the time, these relationships, okay? And we use it in other environments too. So that's what we have to do. Now, incidentally, I have a couple of copies of a paper I left downstairs which deal with this question about this, and it relates to the sun, paper I did back in 1994 at the ICC. And it gives you all the details for you guys who are deep into the physics and want to know all the mathematics and all. You can see some stuff in those papers, and it's data there that relates to this same kind of data that we're talking about here, because the sun's core is a plasma. We know that, okay? I just wanted you to know that. There are a couple of copies if you are that kind of person. That one side. Now here's an important property of the plasma. It's called this wave. It's actually a Debye wavelength, they call it, but it's really a Debye length. Related to it as a length, a distance. Okay? Now that distance is related to a wavelength and the frequency that goes on in the plasma. That's all connected. This equation governs that. It's in error because it needs an e squared on the bottom, but nonetheless, there's an equation for that. And here's that kind of plasma we're talking about, okay? Kind of thing that looks something like that. Thermal pressure is involved, okay? So the thermal pressure has to be considered. Here's how you do the thermal pressure. You need these things. You need these numbers of electrons, these numbers of particles other than the electrons. You need the volume, and of course, a Boltzmann constant.